Now I introduce a differential dynamic programming. Differential dynamic programming is used to solve the nonlinear dynamic system that have a quadratic system dynamic and a cost function. This, for example, this f is quadratic, and g, the cost function also is quadratic. The goal is to solve the system to get an optimal control sequence. However, in a robot application, iterative linear quadratic regulator is most popular. It solves the system that has a local linear dynamic, but cost function still is quadratic. Suppose the state value function at state xk is here, and then follow a system controller or the policies. We select the action, and through this system dynamic, reach the next state xk plus 1, we have a loss L. So if we use a one-step difference, we can express the state as a state xk. In this formulation, we want to minimum select action or select find a policy, make sure this value is minimum. Minimum means no loss. Here, for example, we start from x from one state, we go next state. This state is generated called nominal state. It's generated by the last iteration. And now the new state we want to same as the last nominal state. That means no difference, so we reach the convergence result. However, if they have any difference, we need to use differential dynamic method to further improve this nominal state until reach to the convergence. That's the idea. So we define a difference state in state and the control, and also difference of the action state value function. Expressed in the difference between the cost to go loss and the value function at k plus the k plus 1, I plus 1. That is the next state. By using the second order Taylor expansion, we got this formulation, and here the Q can be expressed as this loss, this is the system dynamic, and this state. So how can we calculate the goal is to select, we find we will search for the optimal sequence of control. So we need to get what's the optimal deviation from the nominal state generated by last iteration. To do so, we just calculate the derivative of the delta Q, and that's equal to 0 to find the optimal deviation of the control. And in this formulation, and here this part is feedback gain, and this is the forward control vector. That means the step size, how far we can go. Just like we in the gradient method. Because this we use the return. I mean, so we calculate the still value function and the Q and the action state value function. We use the from a terminal, and in the backward, the step by step calculate the V and the Q value, and how much loss from the terminal back to the state we are right now. Then we got this deviation. Based on this deviation, we calculate the action, and use this action. Yeah, first use we got this deviation of the action or control, and then we based on the basic control together, we got the actual control used on the current state. And use this is the path, this is the backward path to actually generate the control. Once we get the control, and then we can use the system dynamic to generate the trajectory in the forward path, because we already have this current control. Use this control, we can generate the state one by one, which finally we get a trajectory until the terminal. So that means, to use the differential dynamics programming or use iterative linear quadratic regulator, which include two steps. One step is backward. Backward is to calculate the modification or improvement of on the control. And then in the forward path, use the improvement on the control, we generate a trajectory. That means we generate the state by state until to the terminal. That's the two steps for the differential dynamic programming to solve a nonlinear dynamic system with either the or either the quadratic system dynamic or local linear system dynamic. For more details, please check with this reference. Thank you. Bye.